Hello everyone, we are discussing the testing of fiber reinforced composite materials. In last class we have discussed the tensile testing methods of composite, and now we will discuss the compression testing of composite material. The compression testing is along the plane. Normally in textile material which is flexible in nature, the compression is carried out across the plane. Now, suppose this is one flexible soft textile material, the compression is carried out across the plane like functional textile. In functional textile testing, we have seen in Kawabata evaluation system or FAST, we have discussed the testing method of compression, which is across the plane, that is across the thickness. But the composite material, as these composite materials are stiffer in nature, it is a hard material, that is why here the compression testing is carried out along the plane. Force is applied parallel to the plane of the composite material, and composite materials like fiber reinforced composites, there the load, compressional load is applied in this direction, that is along the plane direction, when these materials are used for structural fabrication. So, this compression here is along the plane, so the standard which is followed here, it is the ASTM D3410 or 3410 M. This method determines in plane compressive properties by applying the compressive force into the specimen at wedge grip interface. This method is most appropriate for composite material reinforced with high modulus fibers. The test procedure introduces the compressive force into the specimen through shear at wedge grip interfaces. Now, let us see the compressive force. It is the test interferences are the test fixture characteristics, test method sensitivity, test specimen preparation, thickness and gauge length of the specimen, gripping and edge effect in the angle ply laminate. Now, this picture shows the compression testing fixture, and when this fixture is disassembled it looks like this. So, here the fabric specimen, that is compression testing, the composite specimen here, this is the actual specimen here it is showing, and which is gripped by the clamp, and which the clamp, the composite material is tabbed, and tabbed portion is being clamped by two clamps, upper clamp and lower clamp, and it is tightened by screw. And during the testing, the upper housing block comes down gradually, and which applies the compressive force on the specimen, and the dimensions are, as I have already mentioned in last class, it is a for 0 degree, that is unidirectional fiber orientation, the width is smaller 10 millimeter, and for other direction the width we can use little bit higher, that is 25 millimeter, approximately 1 inch. The gauge length we can keep almost same, it is between 10 to 25 millimeter. So, compression test specimen thickness depends on the gauge length, expected compressional strength, and the longitudinal modulus. The properties which we can get during compressional testing, it is a ultimate compressive strength, ultimate compressive strain, compressive modulus, Poiseuille's ratio in compression, and transition strain. So, these parameters are similar to that which we have discussed during tensile testing. So, we get curve which is stress strain curve, from where we can get all these parameters. Also we can get chord modulus, which is nothing but the modulus between 2 points, and again like the tensile fracture, tensile failure, the compression failure can be divided, can be termed, or can be expressed by different terms. Here we can also use 3 characters. First character shows the failure mode, that is mode of failure. Second character is the area of failure, and the third character is location of failure. And compression failure can be broadly divided into 2 types. One is acceptable compression failure, which is due to the actual failure of the composite material, and another type of compression failure takes place, that is non acceptable compression failure, which is due to the problem in test method. I will discuss after some time. Now, acceptable compression failure, these failures can be expressed by 3 characters as I have mentioned. Let us take one example. like TAT, which means transverse shear, that is the failure mode is the transverse shear, failure area is at grip, and failure location is at top. So, here we can see that is a TAT, which is acceptable compression failure, means it has failed during the testing at the gauge point, not inside the grip. So, looking at the failure type, we can see this is the transverse shear type failure. The failure is like shear type failure, and it is at the grip point, close to grip point. So, it is at grip. At grip means A, T A, and T means its location is at top. If the similar failure was there in at the bottom, then the terminology would be TAB, transverse shear at grip and at bottom location. The next one is BGM. B, from the first character table we can get B here, it is a brooming. That means during compression the brooming takes place, it splits out. The composite material is actually during compression the brooming takes place. So, failure mode is brooming here, and location is at gauge in between the jaws, okay, in between the grip, and the location is at the middle. So, area is in between that point, this grips, and location is at middle. Similarly, the third one is HAT. H here it shows through thickness, that means the failure is entirely across the thickness, and it is at the grip point and the top location. HAT. SGV. What is SGV? S stands for long splitting, G is at gauge, and V stands for various failure location. It is not at particular location. When the failure takes place at different location, then we can term it as V. So, simply by putting these three characters, we can express the location of or type of failure in addition to the actual value of say extreme point. Now, the failure modes for non acceptable compression. So, non acceptable compression failures are, so first one is say DTT. What is D? D stands for delamination at tab adhesive and at top jaw. At top grip point, the tab adhesive has been delaminated. So, that the test failure is due to the problem in test method, which is not acceptable. Similarly, next one is HIT, through thickness, there is a through thickness inside grip and at top grip. So, through thickness although there is failure, but the failure is within the tab, which is not acceptable. Third one is DIT, that means delamination is taking place inside grip and which is at top location, and CIT, which is end crushing due to high pressure of the grip, the end crushing is taking place, which is inside grip I and at the top. So, this type of failures are not acceptable. After compression, now we will discuss the flexural testing. The standard which is followed is ASTM D7264. So, which is test method for fiber reinforced polymer composite, and it is a flexural testing. So, maximum number of tests per set is 5. Flexural properties are not basic mechanical properties of the material, it is actually combination of tensile, compressive and shear properties. So, whatever the flexural strength we get, these are combination of materials tensile property, compression property and shear property. When a flexural load is applied to a specimen, all these 3 stresses are included, but the material failure is dictated by which the 3 basic stress is the first to reach. Okay. So, here which component will reach first, that will show its compressive or tensile or shear. So, it will show its flexural testing. So, that will be the flexural strength of the material. So, material failure is dictated by which of the 3 basic materials characteristics. Despite the obvious complexities implied, that why is it complex? Because it is a combination of tensile, compression and shear, but the flexural testing is easy to perform. So, although the principle or mechanism is complex, but the test method is simple. Here there are basically 2 types of testing. One is 3-point bending testing, another is called 4-point bending testing of composite. The sample dimensions are, to simplify the stress state in the specimen, shear component is minimized. So, only to keep the compressive and tensile component, we have to minimize the shear component. So, it can be minimized by changing the ratio of length and thickness. So, this is done by making the specimen support, that is support span L, is sufficiently long as compared to specimen thickness. So, if we keep the L by T ratio very high, then we can minimize the shear stress component, and shear stress is independent of length, while the bending moment, that is tensile and compressive stress, is directly proportional to the specimen length. So, L by T ratio we can keep 16:1 or 32:1, these are commonly used, but we can sometime go little bit higher up to say 64:1, just to minimize the shear stress component. And this is showing 3 point bending, where the specimen is supported by 2 points and load is applied from the top at the other surface, that is vertically downward direction, and the distance between these two support points is known as span length. And during the application of load from top side, one side will be compressed and other side will be extended. Now, suppose this is the composite material and these are the bottom supports, and the distance is known as span length, and we apply the force from the top, which is exactly at the center, and this two support points are typically the similar same distance away from the edge of the composite material, the distance L dash L dash will be same, and during bending of this composite, so once this is bent, this beam is bent, so this top side will be compressed and this bottom side will be extended. So, here both compression and extension like tensile loads or tensile deformations are taking place, and we can minimize the shear by changing the length is to thickness ratio, this is thickness. So, 3 point loading system, and this picture shows the 4 point loading system. The 3 point loading system where 2 support pins are there, and this is the sample, and external load is applied from the top. So, the 3 point loading consists of a support point near each end of the beam, near each end of the beam a support point will be there, and one load point at the mid span. So, this is the span length, and at mid span there will be one load, and in 4 point loading system 2 load points at equal distance, there will be 2 load points from the support points, this is this distance support point from the support point, the distance will be equal, and this distance is typically 1/4 of the span length. The general the mechanical strength measured through 4 point bending system is lower than the bending strength measured by 3-point bending system. So, in general this is lower than the 3-point bending system. The value of bending strength. So, if we compare the 4-point bending with the 3-point bending system, so in 4-point configuration the maximum flexural strength is located between the central force application member, that is the two loads which we are applying, that maximum stress will be in between that, and bending moment is constant, maximum flexural stress is uniform, it has no resultant vertical shear force due to presence of 4 points, and in 3-point configuration maximum flexural stress is located directly under the center force application point. So, when we apply the force in single point, the maximum flexural stress will be just below that. The presence of resultant vertical shear force is everywhere in the beam except the right under the midpoint where force is applied. In case of 4-point bending, volume under stress is bigger than the one under 3-point bending system. Now, if we compare the different parameters and their derivations, we can get the stress strain we can express by different derivation, and the test speed is kept 1 millimeter per minute as per the standard, and flexural stress SF in case of 3-point bending is expressed or can be calculated by the formula SF equal to 3 PL divided by 2 BH square. P is breaking load, L is span length, H thickness of the specimen, B is width of the specimen. Okay. Similarly, in case of 4-point bending, the stress will be just half of that of 3-point bending, because here we are using 2 different loading point, and this is expressed by 3 PL by 4 BH square, and whereas strain is expressed in terms of epsilon strain equal to 6 delta H, delta is the deflection at the center of the specimen by L square, and in case of 4-point bending it will be 4.36 delta H by L square. So, modulus can be expressed in terms of LQM by 4 BHQ, and for 4 point 0.17 LQM by BHQ, where M is the slope of the secant of force deflection curve. So, that is the slope of the curve. Now, let us try to see few case studies in case of flexural testing, where we will discuss the effect of twist in the material, reinforcing material, and effects of the treatment, surface treatment with and without MAGPP treatment on flax roving. Now, here 60% means 60% is the volume fraction, and here we have taken the reinforcing roving flax is of with two twist level, one is TPI 8.12, another is TPI 0.73, and the pictures are showing in two different sides. One is compression side, that is the top side from where the load is being applied, and tensile side where it is opposite side. So, this picture shows here as the twist is reduced, the proper penetration of matrix material was there. That is why the sliding of reinforcing material and or matrix failure was not there. With high twisted roving, it is showing some wrinkle portion, that means there were sliding, it was the grip was not proper, and this rovings the flax was untreated. Once we see the other side, tensile side, the composite made from low twisted flax, it is showing there is a proper breakage, proper damage of the composite, it is a crack formation. Whereas, in case of higher TPI, there is no crack formation, simple the composite got extended. That means, there was slippage or sliding between matrix and reinforcing material, proper gripping was not there. So, we can see by stress strain curve, that is the bending deflection and bending stress curve. This shows that the composite with lower twist, the TPI 0.73 shows higher bending stress, whereas the composite with higher twisted roving, that is 8.12 TPI, it shows lower bending stress. That means, the twist restricts the resin penetration in the reinforced fiber bundle. So, due to twist application, the fibers become compactly packed. So, resin penetration was not proper. Now, the effect of the presence of surface treatment, the left side, this is showing the untreated flax, and in right side this picture show the flax treated with MAGPP. During compression, again the presence of MAGPP, that is surface treatment, it forms proper binding between the flax, that is reinforcing material, and the MAGPP, and the matrix material. So, MAGPP helped in proper bonding between the matrix and reinforcing material. That is why the proper breakage, proper load carrying capacity has been improved. Here the twist present in the roving are kept constant. So, from this diagram it is clear that the flexural strength is higher in case of flax treated with MAGPP as compared to untreated composite, and this is true for all the different the fiber volume fraction, that is 40%, 50% and 60% when we keep the twist in the roving constant. Also, if we see the effect of core twist, with the increase in core twist the flexural strength reduces, the reason which I have already explained. After bending we will discuss the next property, which is impact properties of composite. The impact response of composite material was of only minor interest prior to the introduction of carbon fiber as reinforcing material. So, earlier when we used to use the glass fiber reinforced composite, the impact property was not that important, because the most of the applications which we used the composite for mainly tensile testing, but impact resistance is extremely important for composite material for different application. So, impact properties of the fiber reinforced composite sample are evaluated following ways. Okay. So, these impact properties are basically evaluated in two approaches. These approaches are, one is using pendulum type impact tensile testing machine. So, pendulum type impact testing machine, another is drop weight impact test method. So, in pendulum type impact testing machine we have two different types of impact tester. One is IZOT impact test method and other is Charpy impact test method. And in drop weight impact test methods, the sudden pointed weight is actually impacted on the laminated composite surface and the damage is assessed. First we will discuss the IZOT impact test method. So, IZOT impact test method, it is basically there will be one pendulum type impact tester, that is pendulum type impacting surface. Suppose this is our composite material, this composite material, okay, and here in one surface we are making some notch cut, and this is the bottom portion is gripped firmly, this is gripped firmly, and from top it will be some impact, pendulum type impact will be there. The impactor will strike at the top, and due to the pre cut of this composite there will be the damage. Okay. So, this will show the impact strength of the material, and this is the principle which is followed in the ISOD impact test method. So, here if there is a impact, so then there will be some crack, the damage will be there. So, first we will discuss the ISOD impact test method. So, in this method the ASTM D256 or ISO 180 the principles are followed. Minimum number of tests per set is 5. The ISOD impact is defined as the kinetic energy needed to initiate fracture and continue the fracture until the specimen is broken. So, there will be initiation of fracture and then it will continue till the specimen is broken, and total kinetic energy required is calculated. ISOD specimens are notched, as I have mentioned, are notched to prevent deformation of the specimen upon impact. So, once the notch is created, the fracture will be initiated at that point and the fracture will continue. If we do not create any notch, then what will happen? The composite will have different types of deformation, like compression deformation, bending or shear. This type of deformation will be there, which is not actually targeted. The test procedure is the specimen is clamped into the pendulum impact test fixture with the notched side facing the striking edge, as I have shown. I will just show in the next slide, and this is the pendulum where the level of force can be varied by adding extra load. The pendulum is released and allowed to strike through the specimen. This method is similar to what we have learned in tear test, that is Elmendorf tear test principle. If the breakage does not occur, a heavier hammer is used until failure occurs. So, that I have already mentioned, we can increase the weight of this pendulum, and the size of the specimen is 64 length, the width is 12.7 millimeter and the thickness is 3.2 millimeter. Okay. So, this is the width of the material, and this is actually the damage takes place through the width of the material. So, effective width is 10 millimeter. So, effective width of failure fracture. Okay. The position of the sample is that it is a, we have to keep it vertically and the notch is facing to the pendulum. Now, this is the arrangement where the specimen is actually gripped by the support which is holding the specimen, and this is the notch side and the pendulum is striking from the right side, and the striking height is the height from the notch point to the striking point, okay. And this is the test piece. Radius of curvature of the striking edge is this one at the tip, and the angle of the tip of the striker, direction of the impact from the here from right to left side, and angle between the underside of the strike, this is the underside of the strike, and the face of the test piece, this is the angle. So, all this dimension actually affect the test result. The striking point is that upper tip of the specimen, this is the striking point at the upper tip, and the data which we get is the impact energy and impact strength. And this case study where we have carried out the IZOT impact test on the flax PP composite, both treated and untreated, treated with MAGPP. So, the flax PP based hybrid yarn reinforced composite, which is made of polypropylene, which is thermoplastic matrix. So, effect of interface has been studied, which is the impact strength increases with improving fiber matrix interfacial bond. So, when we treat the flax with MAGPP, the impact strength is observed to be increased. Effect of yarn twist, the impact strength decreases with increasing twist level of the reinforcing fiber bundle, because improper penetration of matrix due to higher twist. Effect of fiber matrix distribution, the composites impact strength increases with improving fiber matrix distribution in the composite structure. So, as the distribution of matrix and the reinforcing material increases, the impact strength increases. Next is the Charpy impact test method. So, in this test method, it is originally developed for metal and later it has been used for reinforced plastics. The specimen size is 50 millimeter by 10 millimeter by 10 millimeter. So, each specimen contains a 45-degree included angled notch. Okay. So, this notch is created, okay, which is 2 millimeter depth. So, the depth of the notch is 2 millimeter and placed on other side of the force applying point. So, here in this picture the force is being applied from the top and notch position is at the bottom, just opposite to the load applying point. The striking point is the middle of the sample, okay, and the data which we get here is the amount of energy absorbed by the specimen before it fails. Also, an ultrasonic CT scan unit is used to quantify the extent of internal damage. So, extent of internal damage can also be assessed. Next test method for impact test is the drop weight impact test. So, this is actually this follows the ASTM D7136 method. Minimum number of tests per set is 5. Here in this picture, this is the striking point impactor dimension, and mass, that is the it is a load, there will be free fall of this load with the impacting point, and it will fall on a laminated composite material, and there will be a deformation or some damage will be there. This test method determines the damage resistance of multidirectional polymer matrix composite, which is laminated plate subjected to a drop weight impact event. So, here we have to use laminated plate. Okay. A flat rectangular composite plate is subjected to an out of plane concentrated impact using drop weight device with a hemispherical impactor. This is the hemispherical impactor. The potential energy of the drop weight is defined by the mass and drop height of the impactor. So, if the mass is changed or the height is changed, the potential energy can be adjusted. The specimen dimension, it is a rectangular specimen of length 150 millimeter by 10 millimeter, and thickness is as per requirement. The damage resistance properties generated by the test method depends on specimen geometry, laying of impactor geometry, impactor mass. So, all these parameters will affect the damage property. The impactor velocity, impact force, impact energy, boundary conditions, these are the different factors. The damage resistance is quantified in terms of the resultant force and resulting size and type of damage in the specimen. So, size and type of damage will show the damage resistance characteristics. The damage response is a function of the test configuration. Comparison cannot be made between materials unless identical test configurations or test conditions are used. So, we cannot compare. Suppose if we change the impactor geometry, we cannot compare the impact resistance of two material. So, if we want to compare the impact resistance of two composite material, we have to keep all the parameters as I have mentioned the same, all these parameters should be same. Now, what is the significance? The knowledge of the damage resistance property of laminated composite plate is used for product development and material selection. So, we have to actually know the application. If at all there is some chance of impact is there, then we have to assess the what is the value, what is the extent of impacting force. Accordingly, we can select the material. Drop weight impact testing can serve the following purposes: to establish quantitatively the effects of stacking sequence, fiber surface treatment, volume fraction, processing and environmental variable on damage resistance of a particular composite laminate to a concentrated drop weight impact force or energy. Like we can compare, we can assess the effect of stacking or effect of fiber surface treatment on impact energy by using the drop weight test method. Another significance is that to compare quantitatively the relative value of damage resistance parameter for composite material with different constituents, okay. And the damage resistance parameters are basically it is a dent depth, damage dimension, through thickness location, force versus time curve. So, the damage during impact can be assessed using all these parameters. Let us see, these are the different types of damages during impact testing. So, these damages at the top are actually externally visible damages, and internally occurred damages are this type of damages. So, in externally visible damages are, so depression or dent, split or crack type, or combined split, okay, and combined large crack with the fiber breakage, and internally occurred damages also. Now, the case study here, front side of the failure mode. Here 3 different types of composite are there. One is commonly used glass polypropylene laminated composite using plain oven structure. Second one is that flax polypropylene hybrid yarn based on plain oven fabric, okay. And third one is that it is not plain oven, it is unidirectional fabric compressed composite, which is flax PP. So, yarn is actually laid in unidirectional direction. So, here the in case of glass PP laminate, the cracks are observed here, but for flax PP composite no cracks are observed, okay, due to better interfacial bonding using the MAGPP, the surface treatment. And the back side, this is the glass PP and unidirectional UD, and it is a oven. So, damage area dimension, if we see oven glass composite, its area is 452 square millimeter, then unidirectional composite it is a 960 square millimeter. So, we can see here the glass PP composite will is having highest load concentration as compared to the flax polypropylene composite. And if we see here energy absorbed for unidirectional roving composite, it is a 0.6 times of glass polypropylene composite, and oven roving it is a 0.81 time. So, we can calculate the energy absorbed and peak force also. So, here by this test method we can actually compare different impact results. Okay. We will stop here. In next class we will discuss the fiber matrix interfacial bonding strength measurement. So, till then thank you for patient hearing.